Science College. And the title is Upper Bounds for the Lowest First Zero Families of Caspidal New Forms.
So thank you very much for the invitation. It is a lot more fun to be here as an organizer emeritus. And so I want to thank the organizers for allowing me to come here like this. I will not single out anybody by name, and I will deliberately try not to look at her, but I would like to thank someone for giving a non-number theory talk so that I can give one myself. So the object I'm going to be applying this to are zeros of L functions, but this is really a talk in functional analysis and trying to find good test functions to do certain calculations. It's going to be applied to problems of number theory. I know the talk after mine is going to be doing some stuff on pair correlation, so I will fortunately not have to spend time on that slides. If you're interested, please stay around for the next talk. Background material, mandatory slides you must have at some point. Everybody has hopefully either seen the zeta function or knows enough to just nod their head like this. Oh, yeah. The Riemann hypothesis is true. I'm happy to announce we just got a proof today on the truth of the Riemann hypothesis. Unfortunately, nobody ever sends us proofs of the generalized Riemann hypothesis. They always seem to stop at zeta, but anyways, rather than looking at just zeta where all things are one, you could look at more general L functions. I'll mostly be looking at cuspidal new forms today. Unlike one of the talks, I think it was the talk maybe either, I think 2 before this or 1 before this, I will always assume that there's an Euler product, that I can write my L function as a product over primes, and I will try to emphasize in a little bit why that's so important. So it's conjectured that all the zeros have real part 1/2, other than the trivial ones, and then we can write the zeros as 1/2 plus I gamma. There's a lot of connections to random matrix theory and nuclear physics that we don't really have time to get into today. The next talk will talk about spacing statistics a little bit between zeros of L functions. This is one of the more famous pictures from Odlyzko, looking at 70 million adjacent zeros of the zeta function, and you see this incredible agreement. We know what's going on high up on the critical line, but near the central point, these statistics don't really discern what's going on. And the reason is there's not enough to average over for one L function. If you go high up on the critical strip, one L function has so many zeros and the spacing is getting smaller and smaller and smaller. Near the central point, we don't have that. And so we average over families. We look at a bunch of L functions that have similar behavior, put them together. Okay, so just to give you an example of how we attack problems like this, this is actually the analog of the eigenvalue trace lemma from linear algebra. So why do we care about Euler products? Well, if I write my L function as a product over primes and I do the logarithmic derivative, you should have a Pavlovian response in analytic number theory. You always take the logarithmic derivative and then do a contra integral. If I do that, the log of a product is the sum of the logs. This is something we can handle. And then we just expand out after we take the derivative using the geometric series formula. Only the term 1 over p to the s matters. All the other stuff can be handled very easily. And now when I multiply by zeta prime over zeta and I do my contra integral and I shift the contour, I pick up contributions from the zeros and the poles of the zeta function, and I get this sum over zeros on the left is equal to this kind of weighted sum over the primes on the right. And if you replace p to the minus s with what it really is, you see that the right-hand side, at least if I'm facing like this, yes, is the Fourier transform. And this is why we have sums of phi over the zeros on one side and sums of phi hat over the primes on the other. There's a lot of different statistics you can look at. Stay tuned for the next talk for more on pair correlation. You can talk about spacings between zeros. I want to focus on what's going on near the central point. And if you've done anything with elliptic curves, which when it's in Dyer, you know there's a lot of interesting stuff happening at the central point. And so the statistic that was introduced by Katz and Sarnak is the n-level density. And what you do is you take some nice test function, so it's going to have rapid decay, all of its derivatives will have rapid decay, any type of convergence you need you'll have, and you basically scale the zeros so that they have mean spacing 1 near the central point. And so now the main contribution is going to come from the zeros near the central point. One L function will only give you a few zeros in that window, so you have to take a bunch of L functions that have similar properties. Think cuspidal new forms of the same level and weight, think Dirichlet characters of the same modulus. You average over a family, and the hope is the larger family you average over, the better result you can get. And so the dream is that we will be able to get something about what's happening at the central point, the point we care about the most. To do that, we would want to shoot in a test function that's the delta spike. Unfortunately, the Fourier transform of that is identically 1, which means we would have to do calculations for sums over all primes. We cannot do the number theory that well. That's why I'm not going to give a number theory talk, because I can't do the number theory. I will instead give an analysis talk about what could we do if the number theorists could prove results. So given that I am in a situation Oh, and I realize I am recording this, and I know number theorists can prove results. So everything is now set up so that as you prove results, we can immediately just change the best value we have, and the results propagate immediately in real time. All right, so the Katz-Steiner conjecture is, given a nice family of L functions, there's a corresponding symmetry group. There's groups of matrices that have very similar behavior. And you could give, a 5-week seminar on all of that. 15 seconds should be enough. Okay, so the hope is that in the limit, as the conductors go to infinity, the scaling limit converges to something nice. So summing my scaled zeros, evaluating my test functions at that, summing over all the forms in the family, that should be like integrating my test function against some nice function. And we can write down explicitly what it is. You never want to see calculations in a talk, especially in a 20-minute talk, but they can be written down. They're not horrible until you start to work with them, and then you realize just how bad it is to do some of these calculations. And so it turns out these are determinants of matrices, and the calculations become very bad. It's a real challenge to figure out what's the right way to look at these calculations so you have something that's doable. That is another talk that we will not get to today. The 3 main ingredients to do the number theory is you need to somehow control the conductors, control the scaling going on near the central point. You need some kind of explicit formula to relate sums over zeros to sums over primes and the coefficients of your L function. And finally, you need some kind of averaging formula. It's not enough to convert the problem. If I can't actually execute the sums, it doesn't do me any good. One of the applications of something like this is to try to bound the order vanishing at the central point. And if I use these n-level densities, I get phi of 0 times the average rate is equal to this integral. So I can now get bounds on the average order vanishing. And you actually get, if you can do the n-level density, it decays like r to the minus n. The problem is you have a constant that grows with n. And so no matter how bad you do in your life, you will never get a worse result than what I got, where I was able to prove, at most 200% of the forms vanished to, but I was able to do that in only 15 pages, so it's not too bad. Eventually, the results get better as you go higher up. Eventually, for sufficiently high order vanishing above what you expect, the rank becomes good. But as one of my advisors, Henrik Avanyet, said, you're trying to get better estimates on the empty set. I can prove the empty set has at most this many elements. So it's far from the truth, but it's the best in terms of what we're able to do. At lunch, a bunch of us were talking about trying to find the right metric to study. Rather than looking at the n-level density, it's actually a little bit easier sometimes to look at the nth-centered moments. And so I take my sum over the zeros, I subtract off the average, I'm using physics notation, I raise it to the nth power, then I average over the family. Gobbledygook, there's just something that it is. That's the number theory, they calculate all that stuff. I had several students over a decade working on various parts of this, doing all the technical calculations. Wonderful to have a large number of students. All right, now we can feed that in and we can try to look at what we care about today, or at least what I care about today, trying to figure out how far do I have to go before I see the first zero of an L function. And just in the interest of time, I will only look at L functions that have even functional equation. You can do a very similar change for odd functions. You'll just have one extra zero forced at the central point. One possibility is to look at all L functions. And so not Steve Miller, the Petersonic student, but Steve Miller, the Petersonic student, my mathematical brother, was able to prove that if you have an L function of real Archimedean type, then you don't have to go higher than 14.13. Other people then generalize this for more general L functions. If you go up to 22.661, you will see your first zero. Well, what happens if we take a family of L functions and let the conductor grow, let the level grow? Maybe we can get a better result because we expect that the first zero is about 1 over log of the conductor. So as you go very, very high, you don't expect to have to go so far. So Mester showed, looking at elliptic curves, we get the first zero by up to like 1 over log conductor. Now we believe it's of size 1 over log conductor, so this is quite far from the truth, but it's not bad. It's a result. It's getting smaller as we have the conductor grow. A couple of years ago with one of my students, we looked at one parameter families of elliptic curves that had geometric rank R. So we know the Mordell V group has rank R. And for these families, half the time they were even, half the time they were odd. So we would expect R plus 1/2 zeros at the central point by Birch, Swinnerton, and Dyer. And so we were curious, how big of an interval did we need about the central point to guarantee that we would see on average R plus 1/2 zeros? the answer should be essentially 0 because they should all be there. And so the closer to 0 this is, the closer we are to verifying Birch, Swinnerton, and Dyer. What we were able to do is we could calculate things if the support of the Fourier transform of the test function was at most sigma, and sigma for us was less than 1, so that means these numbers are actually larger than the 0.55. So we actually had a decent sized window about the central point, but we knew we would see at least r plus 1/2 zeros in there. The larger support you can get, the smaller the window. So if you could get a larger sigma, you then start getting closer and closer and closer to what the Birch, Swinnerton, Dyer conjecture should be. What I want to talk about today is looking at the family of all cuspidal new forms of either prime level n, or if you want to do a little bit more work, or better yet, if you want your students to do a little bit more work, square free level n. If the level is not square free, it becomes much, much worse, very technical. And if we look at the entire family, how far do we have to go before we see at least one form in the family whose first normalized 0 is at most this high? We want to see, if I go to this height, I'm guaranteed that at least one form has a 0 this high or lower. And we were able to get some bound depending on the test functions and various properties. I will expand this out in a few moments as to where all these numbers come from. We were basically able to show there has to be at least one form whose first 0 is at most 1/4 of the average spacing of what's going on near the central point. So that was nice in terms of just how high up do we have to go. The better we can do the number theory, the bigger sigma we can take, and the better result we can get in terms of there must be at least one form that has a really low first 0. And that's the question, is how low must that lowest 0 be? You can also look and see what percent of the forms have at least r normalized zeros in some window. And the larger the window, then the more likely you are to have that many zeros. And so just you're reporting on some results, the higher level you use, the better the results tend to be. For a while, the results are actually quite bad. There's at most a 420% chance of having, 28 zeros, in this window. I actually can easily give that proof right now. It's greater than 100%. No. So you have to have at least one full proof in a talk, okay? But eventually these results start to kick in. When you start to put in too many zeros in the interval, then eventually the results kick in and start giving you non-trivial results. And now we start getting, there's only a probability of 3% of having 34 zeros on average in a window of size 0.8. Well, we actually expect there to be less than 1 0 in a window of size 0.8, or maybe 2 because they're symmetric. So this is way above what we would expect. And again, it's because the number theory is not good enough to allow us to use the best test functions. The better the number theory, the better test functions we can put in, and the better results we will get. Okay, so now, continuing, what I want to do is I want to talk a little bit about the construction. How do you actually find the test functions to do calculations like this and get results? So a lot of this is very similar to the paper I did with John Goes years ago, which is very similar to the paper that Mester did. I need a couple of basic facts. The first is the convolution, A star B. The next is the Fourier transform. Everybody has their own accent as to how they speak on the Fourier transform. I was taught the -2 pi I. If you take two derivatives, that's the same as multiplication. Fourier transform converts differentiation to multiplication and vice versa. What's nice is the Fourier transform of a convolution is the product of the Fourier transforms. So in particular, if you convolve an even function with itself, then the Fourier transform is going to be nice. You're not going to have the minus sign, and you'll get the Fourier transform of the convolution is a hat of y squared, which is non-negative. And this is going to help me construct test functions that have certain desirable properties. So we want to create a compactly supported function phi hat of y. We want it to be nice. We want it to be positive or non-negative in some region, and then non-positive in another region. And then that way we can say, well, if we're in this region, since it's decreasing, everything is maximized if we push everything to being at the central point, and it's negative in this region. So if we throw everything away, we're not making things larger. So how do we find such a function like this? It's very hard to construct a function that has compact support. So instead we start off by choosing a function with compact support and not worrying about, I want its Fourier transform to be compactly supported. I start with a function that has compact support and then go backwards and get my initial test function phi. So I start with a nice function h that has compact support. I let f be related to h by rescaling, and that rescaling is telling you how the sigma comes into play. I then let g be f star f, and the reason is g hat is now going to be non-negative. I then let phi hat omega be g of y plus 2 pi omega minus 2 g double prime. And when you go through and unwind this, you get that phi sub omega is just going to be g hat of x, which is non-negative, times 1 minus x over omega squared. So when x is less than omega, this is going to be positive, or at least non-negative. When x is greater than omega, it's going to be either 0 or negative. And so this will give me a desired function. Phi hat omega will have compact support. Phi omega will be positive in the region I want it to be, negative in the region I want it to be. And so what I do now is I look at the nth centered moment. I take my sum over zeros, I subtract the mean. Well, really what I should be doing is I should be subtracting the mean at level n, not the mean in the limit as n goes to infinity. So you just do a little bookkeeping to say that they differ by such a small amount that in the limit you can just replace it and it's no problem. And I just record what that mean is from the earlier calculations from number theory. And so now I have my sum, I've replaced the mean, I have my nice test function, and phi omega of x is greater than or equal to 0 if x is less than omega, and it's negative when x is greater than omega. So if I choose my level n to be odd, then if I look at this contribution, the mean is the positive, so negative mean is going to be negative. If if my zeros are outside omega, then the contribution is going to be negative. So if I throw all that away, I'm making the top line, the left-hand side, I'm making it larger if I throw away those zeros. So it's going to give me the SNA, that term is going to become a lower bound if I throw away, if I have a test function like this. And so now it's crucial that n is odd, because if n is odd, then a negative number to an odd power stays negative. And so now I drop the negative contributions. I don't make the left-hand side any larger, any smaller, so everything is fine like this. If I have no form in my family having a 0 between minus omega and omega, well then I only am summing the zeros up to omega. If there's no zeros in that window, I can just drop all of that, and I just have now negative mean. And then what I'm left with is I'm just dividing by the size of the family, then I'm summing 1 over everything in the family. Well, that's just the size of the family. So that just cancels, and I get, if there are no zeros between minus omega and omega, I get that this quantity is greater than or equal to the quantity from number theory. And so because of, everything has been chosen appropriately, if I can show that there's some choice of omega such that the inequality goes the other way, I have a contradiction. And the only thing I assumed was that there were no zeros in the interval minus omega to omega. So I just now have to see what is the smallest omega I need to choose so that I have this violation. And that's where this result of basically 1/4 comes from. And again, better number theory would allow us to get better results over here. Putting everything together, this is a nice closed form expression that you can play with. I will be trying to optimize and expand this with some students this summer to see what if we looked at more terms, not just the second derivative, what if we played with more involved polynomials? Can we get anything a little bit better? My gut feeling, and I know this is being recorded, my students will hear this, not really. I don't expect there to be major improvements by these small optimizations. For the most part, unfortunately, the big gain comes from changing the level you look at. Changing the test function slightly doesn't really give you that much dividends. You can play a similar game by trying to get balance for how many normalized zeros do you have in a small interval. This is where you actually want to use n is even rather than n is odd. So to be fair, we had one result where we used n is odd. Now we have one result where we use n is even. This allows us to drop various things. What do I mean by that? If I look at the sum over the zeros, what I can do is I can split my zeros into the zeros that are in my interval minus rho, plus the contribution from everything else, and then subtract the mean. And now I'm putting in some kind of condition. I'm assuming that the number of zeros is greater than or equal to the mean over phi of rho. And as long as that's true, my function is decreasing. Then if I throw away the t of phi in the middle, I still have something that's positive over here. I've just made it a smaller positive number because n is even, and I'm not going to decrease what's on the left-hand side, so I'm going to actually shrink it. The danger is if it was negative, if I threw away something that was positive, I could have all those problems. And so this is why we need to use evenness over here. We get a result. It's an interesting question as to which level does better and when. You then get the table I showed earlier that we can get some bounds for what's the probability you have so many zeros in a small window. Unfortunately, the number of zeros we have for this to be useful is so much more than you would expect that these are not great results. hopefully they will be a little bit better by the 42nd, 43rd Automorphic Forms Conference. So, thank you.
Questions for the speaker?
Yes.
Maybe a silly question, but I'm not super